Bienvenidos, Ushamdi, and welcome, CTS230, Section 841 students for the first 8-week term of the fall 2017 semester. This is the Networking 3 course at Anne Arundel Community College, also known as the Scaling Networks V6 course from Cisco Networking Academy. And this morning's video tutorial and solution set is going to be on Packet Tracer Activity 8.2.2.7, where we're now going to transition from Cisco's EIGRP to the open standard RFC 2328 OSPF, or the Open Shortest Path First Protocol. And so we've got a nice activity here to kind of kick things off, where we're going to be doing some basic configuration with OSPFv2. Now, a couple things that we need to comment on real quickly about OSPF version 2. Let's remember that OSPFv2 is classless. So when we talk about class-full routing protocols like IGRP or RIP v1, you'll notice I said IGRP, not EIGRP, but IGRP, RIP v1, those were classful. So OSPF version 2 is classless. So we can do variable length subnet masking, and we can use that CIDR, that classless interdomain routing notation. Also, we want to make sure that we're clear on the OSPF RFC. It's 2328, so you could go out there and Google that and go to the IETF page, the Internet Engineering Task Force page, and you'll see that John T. Moy is the author of that RFC. He is also the author of a couple books on OSPF. They're typically known as the Blue Book and the Yellow Book. And the Blue Book is of incredible value, provides an amazing backdrop as to the thoughts and the decisions that were being made when OSPF was being created. And let's remember that OSPF was a replacement. It was created as a replacement for the RIP routing protocol, right? And the reason that they were trying to come up with a replacement for RIP was that RIP suffered from a number, and still does today, suffered from a number of shortcomings as the internet began to grow. And those shortcomings were a diameter size, right? A diameter of 15 hops. Anything beyond 15 hops was considered infinity. And so again, as networks grew, as internet routing tables grew, right? RIP was not a good solution. And so OSPF was one of the approaches, or one of the efforts that was undertaken by the IETF. The other effort was by the ISO for the OSI model, right? And they have a link state routing protocol as well that's known as ISIS. And so those two link state routing protocols, OSPF and ISIS, they kind of were kind of co-termed in terms of, the start of the development, and again, within, like a year or so of each other. And then when they first kind of made their appearance on the routing scene. So the administrative distance for OSPF is 110. Right? Remember, the administrative distance is 110. And so we're going to be taking a look at some of the data structures that OSPF has, the adjacency table, the link state database, and the forwarding table. So let's go ahead and dive in here to our activity. Again, very straightforward. It's nice that we've got these routers here, so let's make sure that our preferences for our font are 20. Excellent. So we'll be able to see everything. So in this activity, the IP addressing is already configured. That's a good thing. We just need to configure the topology that's here. So use the following requirements to configure OSPF routing on all three routers. So let's just go in order here. We'll start with router 1, and let's give ourselves a little additional space here. We'll come to the CLI. Now the process ID. So let's go from user exec to privilege exec with the enable command, and then configure terminal to get into global config mode. And it's from global config mode that we can now transition into the OSPF router configuration mode. And we simply do that by saying router OSPF1. Now, this is very, very similar, right, to the EIGRP configuration. We would say router EIGRP and then an autonomous system number. But here we're talking about OSPF, and this is a process ID. Now, I'm going to make a statement here. The process ID is locally significant. which means that the process IDs do not need to match for the two routers to establish an OSPF adjacency, right? Now, this is very different from EIGRP. Remember, EIGRP, the autonomous system numbers did need to match. And so this is one of the significant differences. So don't get tricked by being shown output that shows router OSPF1 on one router and router OSPF2 on the other router, only to think, oh, it's the process IDs don't match. They do not have to match for the adjacency to form, right? And you'll notice I'm stressing for the adjacency to form, they don't need to match. Now, there is one very well-known case that's far outside the scope of the CCNA material, but it deals with multi-protocol label switching, or MPLS layer 3 VPNs, when you're using OSPF to peer with the service provider, the ISP, in that MPLS layer 3 VPN scenario. And so know that there, the process ID does take on an additional significance where it is no longer, quote unquote, locally significant. And again, I want to caveat, because a lot of times, I'll say this and then you'll see something a year from now when you're doing your CCNP studies or your CCIE studies, and you'll say, well, wait a minute, I was told by Travis that the process ID is locally significant and here it's not. So again, I want to make sure that I clarify that. So for the adjacency to form, the process ID is locally significant and does not need to match, and that is a true statement. There are other use cases, MPLS L3 VPN being the most prominent, where the process ID takes on another role, right? It takes on a non-locally significant role. So I want to make sure we get that out there. But for the purposes of CCNA, it does not need to match. So we're going to go with router OSPF 10. Now we're going to set the router ID right away. So I simply say router ID 1.1.1.1, and this works, but let's remember that conversation. The same conversation we have with the EIGRP, we're going to have again with OSPF. The router ID does not need to be an IP address, and it is not an IP address. So it doesn't need to be an IP that you have configured on the router. And remember, it is not an IP address. It could be if that is how it gets set. But in most cases, you're going to hard code it. And I always, best practice, always hard code your routing process router IDs, whether it's EIGRP, BGP, OSPF, always hard code it like we're doing right here. And I typically prefer something that looks nothing like an IP address. I prefer that syntax there, like a 0001, because not only is that not going to be pingable, but it certainly is not going to be mistaken for, oh, I've got this configured somewhere on my router, right? And so we kind of achieve the same purpose with the 1111, but that could be, maybe you've got a loopback configured on this router for 1111. So again, I typically go with the 0.0.0. router number, right? So we'll say router ID 1111, and then network address for each interface. LAN interface set to passive, do not use the default keyword. Okay, so the great instruction, that last instruction, we'll tackle that first because that's sort of the lower hanging fruit right now. So the LAN interface is gig 00 is my guess, 172.16.1. So we say do show IP interface brief. And let's get that right. And we see that it's gig 00. So it says don't use the default keyword. So in other words, if I do Control U to erase that, they're not looking for passive interface default. That is not what they're looking for. They're looking for passive interface gig 00. So they want it specific to the interface because the other interfaces will not be passive. Now, we can see that we've got gig 00 and then serial 000 and serial 001 for which we need to do the configuration work with the network statement. And let me make sure these are /30s, and they are. So with the network command, we're going to go ahead and say network. Again, the passive interface, setting the router ID, the network command, just like EIGRP for IPv4, right? Very, very similar. And so here we go. So the network is going to be, let's start with the 172.16.1.0, right? Remember, it's the network ID, not the IP address on the interface, at least in this case. And then it's a /24, so 0.0.0.255. Remember, the wildcard mask is the inverse of the net mask. And very important, we're not done yet, because remember, when we talk about OSPF as a link state database, OSPF provides us with a hierarchy. And this was something we talked about, the John T. Moy, the book, right, where he wrote that they had to come up with a scheme in order to provide scalability within OSPF, because it became simply too much at the time, right? This is at the time. It became too much to have, 50, 100, 200 routers in the same area, because they started to run into convergence issues and update issues. I shouldn't say update issues, but convergence issues, we'll say. And so they had to come up with some sort of a hierarchy. So you have a 2-level hierarchy. And it also provides loop prevention. We spoke about that as well. And that 2-level hierarchy is simply area 0, right? I've got area 0, and then I have all other areas, all other non-zero areas. So this could be area 1. And as we talked about on Tuesday night, this could be area 51. And the requirement is that all other areas must attach. They must be connected to the backbone area. Remember, all traffic from any non-area 0 area, so traffic from area 1 that is trying to get to area 3, it is a requirement for loop prevention purposes that it must transit the backbone area. And the same is true. If area 3 wanted to go to area 51, or area 51 wanted to send traffic to area 3, right, that has to transit the backbone area. And so that's the 2-level hierarchy. So now let me put something up that is typically causes confusion. So here's area 0. Could we have area 1 here and area 1 here? Would that work? And the answer is yes, this will absolutely work, right? In fact, I could put a 3rd area 1 and a 4th area 1. Now, this is probably not a good idea. Again, at least in this little use case here, probably not a good idea, right? Because it's going to become a little confusing, but this will function. That is going to work. And again, when we also spoke about area 0, the text saying that you have to have area 0, and remember, I augmented that statement by stating that you have to have area 0 if and only if you have other non-area 0 areas that are connected. And remember, we started with the sort of the area 51 and the area 1. But if you are never, ever, 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 ever going to have multiple areas, you could simply create a single area and make it area 51. And all of the routers that are in here, this is going to work just fine, right? The problem becomes the addition of another area, and you want to be cool, so you say, oh, we're going to make it area 99, right? This will not work, because that area border router right there is going to realize, hey, I have 2 areas configured here, and neither of which is area 0. And therefore, all of the type 3 summary LSA information that should be going there and that should be going here, generated by this ABR, is not going to be advertised, right? So that is why we need area 0. It's all about, from a architectural perspective, the multi-area OSPF conversation is all about scalability. And again, that John T. Moy book and the passage we looked at where he described the realization that they had to do something like that, or else it just simply would not be scalable. All right, so this is where we have to put in what area, whoops, and I want to, it looks like I just changed something there. What area do we want this to be in? And so we can clearly see that everything is going to be in area 0, although does it say that, or is that in the diagram here? Whoops. It doesn't say area 0, but we can assume, yeah, we can assume that that's going to be area 0. But again, I could say area 51 since we're not connecting to any different areas. So we'll say area 0, and let's see if we get some points for that. And then the other two network statements, network 172.16.3.0, 0.0.0.3, area 0. And then we're going to go with network 192.168.10.5. Oops, sorry. So that would be 1, 2, 3, 4, 10.4, 0.0.0.3, area 0. And again, really the only difference between the network commands with OSPF and EIGRP is with OSPF, we just simply tell the router that this interface, right, or the interface on which this IP address range is configured, and in our case it's just simply a single interface, that interface will be participating in area 0. And remember, we can have, and one of the limitations is, and this is key, on an interface, a single physical interface can only participate in a single area. So I can't say, interface gigabit Ethernet 00 is in area 0, it's in area 1, it's in area 3, it's in area 51. It's one area, right? But a router can participate in multiple areas because a router could have multiple interfaces and each of those interfaces could then be in a different area. So keep that in mind. We can only put a single interface into a single area, but a router which has multiple interfaces can end up in multiple areas. So we've got our commands here, and I think that is it. So let's do this. On router 1, we're done. So again, validation, very important. So let's say show IP protocols. What do we see? Well, we see our process ID, OSPF10, right? We see routing for networks, and again, remembering that this is a little misleading here, right? The routing for network statement is more of a, hey, I've got these 3 network statements configured here. Where's our passive interface? It's gig 00. Here is the routing information for 1111, right? That is us. The administrative distance is 110, and this is the router ID, right? That is our router ID. And in OSPF, the router ID is critical because it is identifying the node. Think of the router as a node, as simply a node in a graph, right? And that graph is going to be what the shortest path first algorithm runs on. And we keep all of that information in the show IP OSPF database in the link state database, or that LSDB. Now this column here, Andrew had asked this question on Tuesday night. He said, well, what's that link ID? What's that stand for? Well, each of these different LSA types, and here we're looking at the router LSA, and take a look at the link count, 3. Now, no coincidence that these are the 3 links that we have configured, because remember, link state, right? It's all about the state of the links on the node. And so that is our node, router 1, and there is a link, there is a link, and then there is that LAN interface right here, and that's another link. So there are my 3 links. That is my link count, right? The checksum is just to make sure that everything is kosher. My sequence number, right? Updates. Have I changed? How many times have I changed the type 1 LSA, right? If I were to add a loopback address and put that loopback address in, and let's do that. No points for this, right? But this is good. We need to be able to understand what is going to make that sequence number change. So remember, I put in 3 networks. So let's get back into global config. I'm going to say interface loopback 0, and we're going to say IP address, and I'll say 11.11.11.11 and 255.255.255. And I'm going to put this command in here, IP OSPF 10 area 0. And I'm throwing this in here, and I'll come back to it later, but right now just sort of let's go with it, right? That's a shortcut way for me to get this interface into do show IP OSPF database, into the OSPF process, and take a look at the sequence number and take a look at the link count. So this is the type 1 LSA. Now, I don't know if this is going to be an option here, and let me see. Oh, beautiful. Really like the fact that they've added this in. So let's pull this up. So here's an option to the show IP OSPF database command is I can say router, because the type 1 LSA, which every single node that's participating in OSPF will generate a type 1 LSA, because that is the LSA that is going to be describing the node in the graph, in this case router 1, and more importantly, as I come down here, router 1's links. What is the state, or what are the states of, or what is the state of the links, right? So, and this LSA, this is what is communicated throughout the area, right? It's in the same area that this type 1 LSA gets generated, and it's limited in the area, right? The type 1 LSA stays in the area, so area 0 in this case. And this is how the information's communicated. So when we look here, you can say, okay, cool. So link connected to a stub network, 172.16.10, stub network, and stub in the sense that it's OSPF is treating it as a stub network. It is the sort of the end of the line. It's a leaf on a tree, that shortest path tree. This is a leaf on that tree. And then here you can see connected to a stub. And so it gives us the information. It also gives us the OSPF metric, and we'll talk about that 10 to the 8th equation that we would use in the auto cost reference bandwidth and how we can tweak that as we move along here. But very important, because this type 1 router LSA is communicated, right? Remember, we talk about the hello packets, the database description packets, the link state request, the link state update, and the link state acknowledgement, those 5 OSPF packet types. And this is when a link state update would get sent out. When I added this guy in here, a link state update would go out saying, hey, you know, I've got a new link, and here is the state of that link, right? And so it's here in the type 1 LSA where that information is communicated. And then router 2 down the path would get this information, and then he would update his link state database with all of this information. And the key is, right, the key, and why the router ID is so important, is in the graph, in that shortest path tree, it is the router ID that is used to identify the node. And here you go right here, link state ID 1111, advertising router 1111. It's the router ID that's being used here. And so when we looked at EIGRP and it had us set the router ID, really the importance of the router ID in EIGRP is when we're doing redistribution, to make sure that we don't create a loop in redistribution, so that if a router saw its router ID and on redistributed information coming to it, it would be able to say, hey, you know, I generated that information, so I don't send that back to me, right? So here it's much more important in just the simple setup, because this is a characteristic, a trait of link state routing protocols, is that they have to have this router ID, which is the link state ID, because it identifies the router within the EIGRP area. So very, very critical. All right, now let's go ahead and we'll walk through on router 2 here, because we want to get a adjacency up here so we can do a little show IP OSPF neighbor output, right? So we'll go from user exec with the enable command to privilege exec config T into global config and then router OSPF10. And let's get that router ID set right away to 2.2.2.2. And we're going to passive, I'm going to make an assumption here. We'll see if we get any points. We do. So passive the gig 00 interface, do show IP interface brief. And again, just like EIGRP, network 172.16.2.0.0.0.255. And then again, what area is this link going to be in? It's going to be in area 0, the backbone area. Network 172.16.3.0.0.0.3. Let me make sure that's right. Yes. All right, and then area 0. And then the final network statement, and there we go. An adjacency has come up, right? We went from loading to full. And I'm going to talk about neighbor adjacencies here and the link state advertisements and how the topology table gets built. And the, once the topology table is in place, then the shortest path first algorithm can run, and we'll show the commands that are used for each of those. So network 192.168.10. Now you'll notice we have .9 here, and the other side is .10. It's a /30, so that means it's got to be .8 as the network ID and .11 as the broadcast address, and this is area 0 as well. And so I believe that is it. Now, let's give ourselves a little more real estate with which to work here to talk briefly about this. So show IP OSPF database, right? Well, now I have 2 routers that show up here. So there's been 2 type 1 LSAs. And again, to see the type 1 LSA, to see what that LSA looks like, show IP OSPF database router, because it's the router LSA. Right? And so here are the 5 links. I'm sorry. So, and it shows router 1 first, and then we come down and we should see, here we go. So this is the type 1 LSA for router 2. And so all of the OSPF neighbors in the same area are exchanging these type 1 LSAs between each other, ensuring that everyone knows everything about everybody else. And this is in stark contrast to EIGRP, where in EIGRP, the neighbors are dependent upon the information they're receiving from the other neighbors. So remember, in other words, in EIGRP, and we kind of talked about this on Tuesday, right? When we look at a distance vector style routing protocol, is let's say that we've got, network X over here. And this is router 1. And router 1 tells router 2, hey, I know how to get to network X. Again, this is distance vector here. This is distance vector, so EIGRP. Router 1 tells router 2, hey, I know how to get to network X. And then 2 says, oh my God, that's so cool. I'm going to tell router 3, hey, I'm router 2, and I know how to get to network X. So 3 over here, right? He has no idea about the existence of router 1. He has no idea that he's recursing to 2 just to get over here to router 1 to get to that network. All router 3 knows in a distance vector routing protocol is router 2 told me he knows how to get there, so I'm giving the traffic to router 2, and that's it. And it's literally like there's this curtain. Think of it as a curtain right here. And router 3 can't see behind the curtain. He just knows that router 2 is telling him, hey, trust me, I can get you over to this network. Just give me your traffic. And that's distance vector. And this is very different from what you're seeing here. We're on router 2, and so that same drawing here, I'm on router 2, and router 2, and we'll say it's router 1, and then we'll put network X over here, right? Or subnet X. And what's happening is router 2 says, hey, I know that to get to the prefix X, I need to go to router 1. And if we had a router 3 and it was participating here, the LSA would get sent, right? And it would send its whole link state database to router 3, and router 3 would see, oh, there's a type 1 LSA from router 1, this node 111, or more specifically, hey, there's a node 1111, and that node he's the one that's proclaiming that, he's the owner of X. So 3 looks at it like this. To get to 1, I need to recurse to 2, and then 2 can get me there. But 3 knows about 1 because he's got that type 1 LSA information that describes the node in the graph and the states of that node's links. And that is the entire concept of link state right there, and definitely in abbreviated form. But you can see, take a look at this, that router 2 is keeping track of all of this information for router 1. And so let's go ahead, and I'm going to bring router 3 online, but I'm not going to bring that link up. So the 192 I'm going to wait to bring up. That way we have that router 1 to 2 to 3, and we can examine that. So the other output we want to take a look at is, what about a show IP OSPF interface brief? And it's not going to let me do brief. So I can do the interface, and there is, and I'm about 100% certain on this, there is a brief option which is highly recommended. And show IP OSPF interface, I'm positive there is. Interface brief, yeah, there is. So, and that's highly recommended. I want to make sure I had the syntax right on that before I told you to use it. And it'll give you a abbreviated version of this. Now, this is definitely good to come in and take a look at, but the brief option consolidates the output that we're looking at. So what do we have here? We see our process ID. We see the router ID, and again, this is for gig 00, and the network type. It is a broadcast, right? It is a multi-access Ethernet segment, and there is the cost. We have the state. So what is my state on this link? Well, there's nobody else there, so I'm the DR. And the same is true of OSPF as it was for EIGRP on this LAN segment, is that we passive the LAN segment because there are no OSPF speakers on that segment. And then here is my designated router priority. And remember, real briefly, the whole concept of the DR is when we're talking about a full mesh scenario, when you're trying to fully mesh things, you've got that equation, n times n minus 1 divided by 2, if you're in a full mesh scenario. And so the DR, from an adjacency perspective, allows additional scalability within OSPF. And then we've got our default priority in that DR-BDR election. And the priority is 1. And you can see here, who's the designated router? That's me. And what interface am I the DR on? It's that one here. And no backup designated router. There is no BDR because there's no other OSPF speaker. And so if we're looking at this diagram, why is router 2 not the backup designated router? Well, a couple of reasons. Number 1 is router 2 has no interface on this segment over here, right? It has no interface connecting it into this LAN segment. So it can't participate in the DR-BDR election. And number 2 is that router 2, if we're thinking, well, wouldn't it be, why is there no DR-BDR election between, oops, sorry, I didn't want to do that. Why is there no DR-BDR election between router 1, IP OSPF neighbor, and router 2? How come it's got this dash here? Exactly. Because what kind of a network type is this? It is a point-to-point network type. And on a point-to-point network type, and it says it very, very beautifully right here, no designated router on this network, no backup designated router on this network, because in a point-to-point network, how many adjacencies are you going to form? There are only 2 points, right? There's only those 2 routers in a point-to-point. Therefore, I don't need to increase the scalability or add that there's the possibility of 70 routers on a point-to-point link. And so that's why we don't see a DR-BDR election here. And then we've got our hello timers. Remember, different than EIGRP. EIGRP is 5, OSPF is 10. The other difference is OSPF is 4 times the hello interval, right, to get to the dead interval. Now this wait, right, that's going to be talking about the DR-BDR election, and so we'll get to that a little later on. That goes a little deeper down the OSPF rabbit hole. And so those are the timer values that we're interested in, specifically these two primarily right here is the hello and the dead, is that it's 4 times the hello interval in OSPF. And an easy way to remember that is how many letters are in OSPF? 4, right? So that's an easy way to remember it. All right, so that's why we don't see a DR BDR is because it's not needed. Again, the concept of the DR and the BDR is to allow for greater scalability within the context of a fully meshed environment so that everybody doesn't have to form full adjacencies with everybody else. Everybody just needs to be fully adjacent to the DR and the BDR, and then you have the druthers who know about the other non-DR and non-BDR routers, but who aren't DR and BDR routers on those multi-access segments. So let's go ahead and bring router 3 up here. Whoops. Let's grab router 3. And so remember, we're going to do the one interface and then take a look at the OSPF database, that link state database. So we went from user exec to privilege exec with the enable command, configure terminal into global config, and what am I doing here? Router OSPF 10 is the process ID, and let's go ahead and set our router ID right away to 3.3.3.3. And then we're going to say passive interface gig 00, which I'm going to assume is that interface they want me to passive. Excuse me. And then the LAN interfaces do show IP interface brief. Now we're not going to do, and of course they would have 2 that are 192.168s. So we're not going to do the 10.4. We'll do the 10.8. So we're going to say network 192.168.1.0.0.0.255, and that's in area 0. And then network 192.168.10. So if that's 6 and it's a /30, the other side is what, 5? Yep, and so we are .4. And then the wildcard mask of 0.0.0.3 and area 0. Now this will bring the adjacency up between, and let's see what kind of debugs we've got going on here. Let's take a look at router 2 and let's say debug IP OSPF, and what can I do? All right, we'll do the adjacency and let's do events, right? So we're gonna, we're gonna get some good debugging going here over on router 2 that will spark some additional conversation. And you can see, and did I not get that right? 192, oh, and I did the wrong network, didn't I? I did, I didn't want that done. So let's do this. We'll say Control A, no network, and that should take that interface down. And I wanted to do the 10.8. So 10.8. Let's get back here. There we go. All right, so it went from loading to full. We take a look here. And so this is nice to take a look at because it kind of gives us an idea as to what's going on. So we can see, and let me go ahead and kill this real quick. So U all for undebug all. And so if I roll back up here and we look at the debug, this is where the hello was received from 3333. And then we get the database descriptor. So you had the hello packet, right? We received the hello packet. Then we have the database descriptor packet, which moves us from the down to the init state, where we're going to have the master and slave election. We realize that we are the slave, and the semantics of this are well beyond CCNA. So we'll just leave it at that the database descriptor packet is where we have that master-slave election. Then we have the database descriptor exchange, right, where the header information is provided, and if the other router says, hey, you sent me the header information for the LSAs, but I need the full LSA, and then it will do a link state request for the full LSA. And you can see we go into the exchange state, right, and then we transition from loading, and we should see, here it is right here, from loading to full, right? So we are now considered fully converged, and then as we're debugging, you can see every 10 seconds, right, we're going to be getting hellos, and we're going to process those hellos when we receive them. So now on router 3, if we were to take a look at the OSPF database, and I was to say, show IP OSPF database, whoops, show IP OSPF database, you can see that we now see 3 routers here, right? So again, it's interesting. 3 is not connected to router 1 right now, right? There is no connection there. 3 is connected, and if I was to say show IP OSPF interfaces, and it looks like Packet Tracer has stopped, and hopefully this is not going to kill the session here. And something to do with Firefox possibly. Let's see, it looks like we may get hung up. So if we do get hung up, that's okay. Yeah, it's going to have us close. So we're at 91. The only thing we were missing here was the network statement for the segment between router 1 and router 3. And so it looks like there's been a premature end to the activity here, but that was everything. What I was going to pull up and what I really wanted to talk about was the fact that router 3 in its link state database will have the type 1 LSA from router 1 describing the node and all of its links. And so we'll pull back real quickly here. Let me see. Let's go AACC 2017 and 8227. So we'll bring that activity back up just briefly here. But anyway, that's what I wanted to say was that router 3 would have that information about router 1. And let's make this a little larger here with Control I. It would have that information in its link state database, right? Okay, well, that is going to wrap up Packet Tracer Activity 8.2.2.7. Remember to add that last network statement in area 0 for that 192.168.something.4, maybe 10.4, I believe. All right, thank you so much for watching. Enjoy the weather and the weekend, and I will see you on Tuesday night.